While thinking about tutorials on musical production with Supercollider, I thought it's the right time to talk about dynamic range compression, because this is a task that we deal with at every step of making sound recordings, be it production, mastering, or mixing, unless the music that we work with is not meant to be recorded at all. Yeah, some kind of acoustical classic music usually. And I would like to talk about compression, of course, from a musical point of view. Look at compressors as musical instruments. It's an instrument that can change aesthetics and semantics of our sound dramatically. Take a look, like here's a compressor that we have. You can see this is almost uncompressed signal. It's intelligent, rather gentle. Yeah, this preset just plays us the dry signal. It's like some cool guy like talking, chit-chatting with us about something. Yeah, but this one is it's a hooligan. Yeah, definitely. It's a rude boy. Yeah. And this one, I don't know, it's some psychopath, yeah, that does something dangerous to our ears. But we know how to fight that. We know that. I will show you. In Supercollider we have some unit generators that do compression, like Compounder unit generator or Lookahead limiter. Also, there are numerous algorithms in Faust, I guess most of them are now included in the latest Faust libraries distribution, which can be compiled as Supercollider unit generators. But I would like to take a look at what we can do without them, just by specifying our compressor in a synthesis definition format. So yeah, so here's the source code for this root boy, and let's take a look at it from top to bottom. I hope this will not take a lot of time. So first we have here, first important thing is this EnvDetect, yeah, envelope detector. What we do here, we take the factual values of the signal that we have here, signal at the input. Here I take it with the sound in from digital audio workstation, which just plays a loop. Then I high pass this signal. This is optional thing. Some people do that if they don't want the low frequency information, well, part of it, to affect the results of compression. Because the thing is that actually we get the results of analysis, this amplitude curve, by removing high frequencies from the signal. Yeah, unless the high frequencies in that side chain, the result of the analysis, less harsh, less dirty will be the compression. Yeah, but we might also want to high pass that thing, yeah, to a certain degree, so that compressor works on middle frequencies. Yeah. So this is the thing we usually have in some compressors. EnvDetect is one of the unit generators that analyze amplitude. Usually what they do is, it can be represented by this line. It's something like, we take absolute values and then use one pole filter or several other filters, certain low pass filter of different kind with some specific control. Like for example, this Lagud uses one pole filter with coefficient controlled by whether attack or release time, and that depends on whether signal rises or falls. Yeah, when signal rises it uses one time, when it falls it uses another one. So that's how it works. So it can be a cascade of some filters and so on. Yeah, so absolute values smoothed out, yeah, averaged out. It can be an averaging filter as well. And of course at this level we can do something to it. I don't know, like calculate power of this signal, calculate this signal to the power of something, exponent or square root, and so on, like freak out like psychopaths. And even some hard things like, I don't know, like slew limiting, or there is a ramp unit generator, Supercollider, that does linear ramps and so on. It's all about aesthetics. Like let's compare these two that I have here. This is a hard compression with EnvDetect, yeah, very harsh, over exaggerated compression. And let's just switch to this Lagud thing. Lagud. You see, it also does a compression, but it's a bit harsh. We have to tweak the release time, for example, yeah, by smoothing out that output of that filter. And also you might hear that we have that peak, like over exaggerated. Yeah, we can control that with the tag time by increasing or removing, but not only that. Well, I will talk about that just a bit later. So what we do next is, as you can see here, we convert this envelope to decibels and compute excess over the threshold, which is here represented by the threshold control, which is in decibels from 0 to minus 120. Just for fun, of course, you don't need that minus 120 decibels. I'm just freaking out a bit. Let's take a look at some plots. Here is the sinusoid. Here are the absolute values of the sinusoid, yeah. So it was going like from 0 to 1, then to negative. Now it's positive thing. Let's compute decibels. Let's use this ampdb function. You can see now that where it was 1, it's now 0, yeah, and all other values are negative, yeah. And when it was 0, it now, well, does something weird here, but I guess that's because of the limitations of this plot, or this plotter functionality in Supercollider. Actually, we can take a look at this array of floats and the result of this calculation. When we have 0.1, which is 10 times smaller than 1, yeah, we have minus 20 decibels, yeah. 10 times lower than that, minus another 20 decibels, yeah, and so on, minus 20, and so on. And when we have 0, it's minus infinity. Of course, unit generator will not return us minus infinity, even though I don't know, because even if it would, Supercollider should suppress that. Current versions, as to my knowledge, but I guess it's not even doing it. I didn't check. So that's how it should be. Like, this thing should, well, approach infinity, but instead of that, it should be something sane, yeah, something that in the context of the task that we do should represent a minimal, something like minimal possible value, minimal sane value, let's say like that. And once we have that, we converted that to decibels, then we compute that excess thing, yeah, over the threshold. Threshold now is in decibels. This threshold is now in decibels, and our signal is also in decibels. So we want to compare those two, yeah, and we do it like this. Here's an excess, now without decibels, just a linear. Here's that sine-ask, aforementioned sine-ask, and excess with the input parameter of 0.7. Let's take a look what happens. Here's the sinusoid, and as you can see, what we have done is something like this, yeah. we took this part, cut it, yeah, and place it from 0 to the end. It was from 0.7, yeah, so now it goes like from 0.7 to 1, yeah, it's 0.3, yeah, so now it goes from 0 to 0.3. The same thing we could get just by subtracting the clipped value with this 0.7 from the original signal. And in decibels it would look something like this. Now sine ask is in decibels and our excess is in decibels, yeah. Excess input parameter is in decibels. So for this signal, for this one, we would get something like this. Something like ranges are different, yeah. Wouldn't be that easy. Okay, so it goes from 0 to 20. This is like it's like something like this. 0. I'm doing the fancy things here, yeah. Okay, so I guess you got the idea, yeah. So but we don't need these guys. We don't want to have this. So that's why the next thing, let's go back. Next thing here is this max operator. It's a clipper, so it will clip anything below 0. Anything below 0. Let's take a look. Let's go back again here, and I have it all lower. So this is with max 0.5, yeah. Now we removed everything from here, and this goes from 0 to 20 decibels now. This is what we have. Above this, minus 20 decibels threshold. We had a signal like all over the range, yeah. It was going from 0 to 1 and so on, whole range that we have, yeah. Now we put we converted it to decibels and put the threshold to 20 decibels, and now we got just that, from 0 to 20 decibels. What we want to do then is to specify a certain ratio, yeah, and according to that ratio we want to compress our signal. Ratio, for every ratio decibels over the threshold, we will get 1 decibel at the output, yeah. So when that means, like, when the signal goes off, ratio is the variable, yeah, like let's say ratio is 2, that means for every 2 decibels over the threshold we will get 1 decibel at the output, yeah. But these are purely technical. It's quite not relevant to what we do. I mean, these are just technical things. If you know them, yeah, it's good. But if you don't actually need to do this, because this, once it becomes a musical instrument, you don't care about what is the amplitude of that string of a piano or something like that. You just listen to it and play with the timbre, and you start doing semantically meaningful things, yeah. According to your artistic language. So we do it like this. This ratio reciprocal minus 1 does just that. You can see that once we, let me show it in its entirety. Our signal is now in decibels here, and we multiply it by minus 0.5. That means a ratio of 2, yeah. Ratio of 4 means we will multiply it by minus 0.75, yeah. So let's take a look. For example, it was from 0 to 20, yeah, before. It was from 0 to 20. And now, what we have done with this multiplication, first, we changed it, so now it goes from 0 to negative, because the result is negative, yeah, and it was to 20, now it's to 10, yeah. That's what we have done with the ratio of 2, ratio equals to 2, yeah. And we can see also the most meaningful here, the most meaningful or most effective differences here in these values are from 2 to 8, let's say, yeah, and not even 2, like from 1 point something, 1.5, let's say, to something like 4 and 5, and these are the most used ranges for dynamic range compression. And why? Because you can see that there is not a big difference between 8 and 20. Yeah, 8 and 20 gives just a little difference here, like about 0.1, yeah, something like 0.1, less than 0.1. Yeah, but here, well, the biggest range of changes is happening here, like from 0.5, let's say, something meaningful, to something like 5, which will sound rather harsh already. Okay then, so we have this signal. It goes from 0 to -10, and keep in mind these are in decibels so far. What we do next, we do this, convert it back to linear. This is our result of the analysis. Now we have the signal that will compress our original, and we will do that just by multiplying input signal by this one. And what will that mean? It will mean that when this thing is equal to 1, there will be no effect on the input signal, yeah, it will pass as it is. But when it's lower than 1, then we will start to squeeze the signal, yeah. Also, here is a cheap way of applying a knee, so-called knee smoothing, of how we proceed from this point where we don't compress to the point where we start to compress, yeah. In some cases we would like to smooth it out. I wouldn't say it's that much of a aesthetically important effect, not quite, but if we will use it rather insanely we might get interesting musical results, because and I like just this one, because in some compressors you will find something like interpolation, accurate interpolation by table lookup or something like that, which will not lag the signal. Here what we do looks just like this. You can see this is harsh, this is a lot, this is too much. I didn't see anyone doing something like this, yeah. 100 milliseconds lag, too much. I saw this way, well, I kind of came up with this thing intuitively, but I then saw a bit later, I saw that in the code of Julius Smith's compressor, and he uses it so that the lag is equal to half of an attack time. An attack time range is usually from 0 to something like 20 milliseconds. Might be a bit bigger, but that's how it is. Also, it would be something like 10-15 milliseconds maximum usually in this case, but I like to put it like insane values, just because I want to play with the different transformations that compressor can do to the sound. You can see with this insane, let's put it to 1 point, something like this. It's just very accurate smoothing, and only from one side, yeah. That's why people do interpolation, because they want it to be kind of symmetrical, yeah, with this type of input. But that doesn't play that big role to me. This is much more interesting. It will change the aesthetics. I will show it now how it works. Okay, let's now take a look how these guys affect the result. This is to 10 milliseconds, something like around 10, and this is around 100, yeah. And ratio is -24. Okay, why not? Let it be there, even though not that necessary. We can also start compressing by trimming instead of using the threshold, but well, that's just one of the different approaches to it. Some compressors don't even give you the threshold. Instead, their interface telling you just amplify shit and you will hear the effect. And this might be better because it kinda doesn't need gain compensation later, yeah? Because if we do it like this, for example, okay, this is something like -6, yeah? And now let's, you see? Or let's do it like this, a limiter, yeah? Yeah, we don't care about the gain compensation later, yeah? So this might be a good idea as well, so that I include it. But if we use threshold, then we actually make it quiet. So next we have to do this, yeah? And I wanted to show attack time, yeah? Okay. By making attack and release time bigger, we will get smoother signal. Then the ratio, as you can see, the most of the effect, when the ratio is equal to 1, we don't get something. We don't get that much. Let's remove this gain for now. So it starts to affect the signal once we start to approach 2. This is already, well, quite audible effect, yeah? And when we go further, this becomes really harsh, yeah? But here, not a big difference, yeah? The next thing is this knee. As you can see, here I also multiplied by attack, as Julius Smith did in his code in Faust. Maybe I have it, I was looking at this compressor sleep. Knee control. Yeah, you can see here is the code from Faust compressors library, and he uses this knee smooth, which is in turn is C smooth, and smooth is kind of same thing as lag in Supercollider. It's a one-pole filter, yeah, and he uses attack as a coefficient. He uses attack divided by 2, and this is the same thing as lag. This tau to pole, it means like you would take time in seconds and convert it to a coefficient. Okay. So I guess it's clear about the knee, yeah? Okay, then a ratio, I showed that. Knee, Lookahead. Okay, let's take a look at these two things, Lookahead and saturation. The thing is that I don't only have this part to compress the signal. I'm not only using this part to compress the dynamic range, I also use this soft clip thing here. Let's say I want to exaggerate the attacks. I want to have those harsh attacks, and so I'm increasing the attack time so that part of the signal will pass through, yeah, will go uncompressed, and then compressor will kick in and do its dirty thing. The thing is, the problem is that you can hear now and see that attacks are too big. The ratio of peaks to averaged values in this signal will be not appropriate. I mean, we will not be able to make it even loud enough so that it will compete with other instruments in the mix, and overall that will put unnecessarily big dynamic range and quiet recording. So if the person who listens to music, for example, part of this music, will make the recording louder, yeah, will then get that peak striking his ears, you might damage the hearing mechanism of a person. The most important thing that suffers from this type of accidental clicks, yeah, not just tiny clicks, but this type of like a bit long percussive strikes, is a neural part, yeah, those hair cells inside the inner ear of a hearing mechanism. There are converters that convert the mechanical waves to electrical impulses. If they are broken, then we don't hear shit. Neurosensorial deafness, I guess that's the translation. So they get squeezed by the vibrations of a liquid inside of the cochlea, the inner ear. Yeah, there is a basilar membrane, and inside of it there is a corti organ which has those hair cells. The liquid inside of the inner ear, inside of the cochlea, squeeze that thing, and if it happens very fast, then they might broke, and then they stop to transmit shit, and you don't hear anything. Yeah, this is the most serious damage to hearing. That's why you should never stand behind the big loudspeakers, because near the big loudspeakers, they will probably damage your ears. So we shouldn't do that in the recording. How do we fight that then? One of the simplest things is to use inertialess compression. Yeah, the thing was here, depicted here, this averaged signals. It can also be called a compression with inertia. Yeah, but this soft clip thing, nonlinear wave shaping, yeah, another way of nonlinear wave shaping, which can be implemented just by indexing it to a table. Yeah. The shaper unit generator in Supercollider does that. You can just provide an arbitrary transfer function. For example, this soft clip can be done like that, or you can provide any other sigmoid like. Yeah, soft clip. This soft clip looks like this is the soft clipping. Yeah. Well, one of the forms of it. Soft clip does following. It's linear in the region from minus 0.5 to 0.5. Like, there is a region in which it's linear. I don't know if this is that or a bit different shape, because you might guess that there are different shapes of it. Yeah, this is different than this one. Yeah. So soft clip in Supercollider, if I'm not mistaken, is linear from 0.5 to minus. Oh, this is not that range, by the way. We should be from minus 1 to 1. Is there anything from minus 1 to 1? Yeah, here's the thing. Tongue sick. It's a bit. Okay, you might get idea. Let's say that this is 0.5 and this is 0.5. Yeah, this minus 0.5. It will be linear in this range, and will start changing the shape like this, something like this. Above that, here, and symmetrically here. You can also play with this thing by biasing the signal, by adding a e.t.c to this before the soft clip. This will change the aesthetics as well of this saturation. I don't do it here, but you can do something like in plus e.t.c with a certain value. There will be a certain value, or you can just use a control, something like this. I don't know, like bias. Yeah, bias. Let's do that. Are we okay? Yeah, and add it here. Bias. Yeah, and a spec, of course. So we have this gain control. I increase the gain, and as you might guess, this thing, this soft clip, just clips those extra peaks, yeah. And since they are short, they are rather short, we don't get that much of distortion. We can also use just a hard clip, yeah, that clip unit generator, like clip 2, for example, or something. And if the part that is over the threshold, if the peak is rather short, it in lots of cases will do it seamlessly. Yeah, in some cases this is actually the best way to compress, because the thing that we should be very careful about is, of course, compressing the signals that have some spatial picture inside. Yeah, well, the obvious thing is a master bus. Yeah, this should be considered very carefully, whether compressed or not. In some cases, the most gentle is actually just a hard clip for a master bus, because the first thing that you will ruin if you compress it wrongly, well, compress too much or not in a proper manner with not the proper settings, because you don't quite want actually to compress the master bus usually. But if you do, then first thing that will suffer is a spaciousness. So clipping will give you some and different components, will add dirt to the aesthetics, but it will not ruin the spaciousness. Yeah, it will not ruin the spaciousness. Okay, so this is one of the ways how we can compress. We first compress with inertia, and then we finish the job with soft clipper, yeah, inertialess compression. Yeah, and by the way, here's the bias. You can see a bit different, like how it affects the bass. Without it, a bit different timbre. Generally, it's a different balance of odd and even harmonics that this thing would generate for a sinusoid. Okay, but there is also another approach which might be more preferable if you want to compress that hard. It's a lookahead. What is a lookahead? Usually it's just delay of the signal that is to be multiplied by the sidechain. Yeah, delay of our input signal before the multiplication. This delay will not affect the copy that will go to analysis, only the copy that will be multiplied by analysis results. And this way we will play with how in time the analysis result and the signal, our output signal before multiplication, will align in time. Yeah, and this might affect the result of compression dramatically. So this is a very important thing. For some reason I don't see it in lots of compressors in a way that I like to use it, and so here's the way I like to use it. I like to just play with that thing frivolously. So let me just remove this saturate thing, and let's take a look at levels. By the way, here are the levels. You can see it clips. Yeah, if I will put the saturation back, it doesn't clip. Yeah, this is a saturate control. It's just a select unit generator that selects whether to output a clipped signal or unclipped one. Yeah. So now I'm outputting the clipped signal, yeah. But let's change the delay time for this guy, this in guy, before the multiplication, yeah. So here's the delay and here's the multiplication. So once I start to work on it, you can hear now it sounds more gently with this Lookahead than without it. You can see this is without a Lookahead, yeah, without a Lookahead, and this is with the Lookahead, yeah. We can see it starts to clip a bit less than without it, and it's a different sound. It's a different sound. You can hear now it doesn't clip at all, yeah. And if we put it to 1, it's just a totally different thing now, yeah. Okay, so this is a look ahead. The last thing, the most important thing that I would like to talk about. This part, the analyzer, yeah, the analyzer that results with something like this, doesn't have to be just for compression, yeah. We can separate it totally as just an analyzer unit generator, feed it with an arbitrary signal, and then use the results of the analysis to drive any parameters of any other synthesis nodes, yeah. And this is the most beautiful thing, and that's why I focused on these plots here, showed what happens at different stages, so that we could then use this correlate of loudness, which is one of the most important correlates of emotions, yeah, of emotion. By having the results of loudness in this form, we can then drive, I don't know, like modulational index of some modulational synthesizer. We can drive some microsound processes, yeah, the temporal characteristics, some I don't know, something like, oh, I will show, by the way, granular compressor a bit later, that I have. So we can do a lot of things like that, yeah. But that's a wide topic, that's for later. I will use something like that here and there later. So hope this will be useful to you. This is one of the fundamental instruments in sound production. Do something of your own, play with these things, find out something interesting, and let us see what you found. Yeah, so till next time.